One of the most foundational pieces of calculus is something called limits. So we're going to start by looking at limits of sequences. We've discussed sequences before in chapter 10. Now, remember, a sequence is just a list of numbers that have a pattern. So if we have a sequence that is listed where each of the terms is given with this explicit formula, what that gives us is 1, 1/4, 1/9, 1/16, 1/25, and on, so that every term looks like 1 over n squared. Now, as you get bigger and as n gets bigger and bigger, what you see is that the fraction is going to get smaller and smaller. So what we do is we make something called a limit, which tells us where it's going. So a limit isn't actually where it actually gets to necessarily, but the limit tells us where it's going. And the way you write a limit is you write LIM, and then we're going to write our limit as n goes to infinity this time. So you have whatever variable you're working with and tell where you're going. So we want the limit as n goes to infinity of this sequence. And we can see that as n gets bigger and bigger, that the fraction gets smaller and smaller, which means that the sequence is heading towards 0. It gets closer and closer and closer and closer to 0. It doesn't actually get there, but that's the limit. The limit is where it gets close to. Now, there's a fancy definition that I'll give you for limits, but we're not going to delve into that too much until you get to calculus, but I'll go ahead and give it to you. So the sequence AN has a limit L, we'll call it capital L, if and only if, that's what this IFF means, if and only if, for every, that's what the upside down A means, epsilon greater than 0, there exists an n such that the absolute value of the difference between the sequence term and the limit is smaller than this epsilon whenever n is greater than capital N. Alright, so that's a lot of mumbo jumbo. What does that mean? Well, what it means is that if you have this limit L, then the difference between your terms and this limit L is a tiny little number epsilon when you get big enough. So when your term is far enough along the list, you can subtract your limit from the term and you're going to get it smaller than this tiny little thing. Epsilon's usually something like 0.01 or 0.001 or something like that, where it's very small value. And in calculus, we'll get a little bit more specific about this, and as you get into higher mathematics, you can do things where you find the epsilon and such, and there's some examples of that in your book. But for the most part, we're going to just know that what this means is we're getting closer and closer to that limit as we get farther and farther along in the sequence. So we've got some theorems to go with this to help us calculate this. And the first theorem that we're going to look at says that if you have a sequence where we have 1 over n to some power p, where p is a natural number, where that means natural number, so that's like the counting numbers, then the limit as n goes to infinity of that sequence is equal to 0, which is what we saw here in our example. This is a specific example of what this theorem says. Now, we also have lots of properties, and if you look in your book, on page 543, you see some of these properties. So if you have sequences, and they have limits, then you've got these properties that'll work. So the limit as n goes to infinity of a constant. So if you say, for example, the limit as n goes to infinity of 5, well, it's always 5, so we're listing it out. So the limit is actually the constant itself. Then if we have the limit of two sequences that we're adding together, we can add their limits individually and be able to solve that. Or if we're multiplying two sequences together and then taking their limits, we could do the limit first and then multiply, or same thing with dividing. If we're dividing the two sequences and then taking the limit, we could take the limit individually and then divide it. Then another theorem here, if we have a constant times the sequence, then we can pull the constant out front, take the limit of the sequence, and then multiply it. So let's look at a couple of examples here so that we can see how this works. So if we have the limit as n goes to infinity of some sequence an equals 64, if I can read my writing here. And we know that the limit of some other sequence b equals 16, and we want to find the limit as n goes to infinity of 3 times an over 2 times bn. So with all those properties we just looked at, we can split it up. We know that if we're dividing these two sequences, that we can go ahead and divide the limits. And we know that if we have a constant multiplied, we can pull it out front. So we know this number is 64. And this number is 16. And of course that's a pain to multiply out, so let's just simplify it while we've got it in this form. And I hope you guys know how to do all that. That's a long time ago. So our limit of this is equal to 6. Now sometimes you have to use some little tricks to do your limits. So I'm going to show you one with one such trick. Let's say we're looking at two sequences that are given by these explicit formulas. Right. Now, we know we can split it all up individually, but we don't really know, once we get down, we'll have the limit as n goes to infinity of n squared, and so on and so forth, and we don't have anything for that yet. So we do have that one that we looked at the very beginning, where we said we have 1 over n to a value, and that would give us our limit. We know that. So a little trick that you do is get to that point. And remember, you can always multiply by 1 in disguise. So we're going to multiply by 1 over n cubed over 1 over n cubed. Now, why that? Well, that's our highest value here. And if we multiply through this, we'll have no more n's on the top. We'll have a whole bunch of n's on the bottom, fractions of n, so that we can use that first theorem we talked about. So when we multiply this, it looks like the limit as n goes to infinity of, I'm just going to distribute it right across and simplify. Okay, so now we know we can split a whole bunch of this stuff up. We can pull out constants and write it all out. So I'm going to go ahead and split it all up in one fell swoop here, and you need to pause it and look at it and make sure that you've got how I got all of this split up like this. Okay, so we use that quotient rule and the multiplying times a constant rule, and the adding and subtracting rule, and split it all up. And notice here, we would be taking the limit as n goes to infinity of 3, and we know that that's just 3, the constant. That was one of our first properties. So when we do all this, that means this one's 0, this one's 0, this one's 0. This is all by that first theorem we talked about. This one's 0, this one's 0. So we end up with 0 over 3, which is equal to 0. So our limit as n goes to infinity of this is 0. Now remember, if you get 0 over 0, that is not equal to 0. That's an indeterminate form, and you'll have to figure out a different way to do this. So make sure it actually looks like something like this, where it actually ends up being the number 0. So limits of a sequence, read over those properties and those theorems, try some practice problems on your own.